Well, thank you, Giulio, for inviting me to this meeting. The title of my talk would, I think, have been of great interest to Cyrano. He invited me on a number of occasions to Saclay to talk about this very question. And the question really is, does Paris's replica symmetry breaking solution, which solves the Sherrington-Kirkpatrick model, does that extend down to 3 dimensions? And I will be arguing in this talk that it stops working in the world of less than 6 dimensions. So it doesn't work in physical dimensions. Now, these are just arguments. I have no proof, and the debate seems to be never ending, but this is the essence of what I will be at least arguing. Now, my talk is on 2 topics. The 2 topics are both the normalization group calculations, but they have quite different character. The first one was done in conjunction with Wenlong Wang and Helmut Katzgraber, and it's a real space renormalization group calculation. And the second topic is done in conjunction with Nick Reed. Nick Reed's got this fondness for collaborating with people called Moore, and we wrote this paper, and this is a perturbative renormalization group calculation, and it has the advantage that we know what we're doing, we can control the approximations, but almost as a consequence of that, the results are limited as to what they can tell us.
In the previous paper, you don't know what you are doing?
Well, it's a real space calculation, so you never know what you're doing. There's no small parameter, so there's always issues. So what is the problem? Well, the problem is to understand the Edwards-Anderson spin glass Hamiltonian, which is shown here. Jij is the coupling between the spins. In the Edwards-Anderson model, they're on nearest neighbor sites. The spins take the value plus or minus 1 as their Ising spins. And the Jij are just random but fixed variables drawn from typically a Gaussian distribution, but other choices are available. The plus minus j choice is often used, especially in numerical studies. And what Edwards and Anderson claimed, in fact demonstrated with approximations, that there was an order parameter, QEA, which was a long time limit of this correlation function here. So below a certain temperature Tc, the system in a sense remembers its initial orientations. Its overlap onto its initial orientation is QEA, and it was non-zero. Now, one thing we know about this problem is there's no transition in 2 dimensions. The mean field limit of the problem is the Sherrington-Kirkpatrick model. This is a model in which every spin interacts with every other spin. You have to scale down the extent of the coupling to get a finite transition temperature. And it's this model which forms the mean field limit of the spin glass problem. And it has been solved exactly by Giorgio, and it's now been shown to be exact. And Cyrano and Kondo and Temeshvari studied in great detail the Gaussian fluctuations about its mean field limit, and these are very, very difficult calculations, and because they are so difficult, the normal program of calculation where you do the mean field theory, you do the Gaussian fluctuations, and you use those propagators derived from the Gaussian fluctuations to compute higher order diagrams. That program more or less has got stuck at this point here. Because of the algebraic complexities, higher order effects have not been investigated within the spin glass phase. Well, there are 2 pictures as to what's going on in spin glasses. There's the replica symmetry breaking derived picture, and there's the droplet picture, which begins with the work of Macmillan and Alan Bray and myself and Fisher and Hughes. It's very old, this work, dating from 1983 to 1986. And whereas in the replica symmetry breaking picture of Parisi, there are an infinite number of pure states, in the RSB picture, there are just two pure states. In fact, the droplet picture is really just states that the spin glass is a bit like a ferromagnet. And what one tends to study to bring out the difference between the two pictures is this overlap Q, which is the overlap between two copies A and B of the system. And if you look at the distribution of Q, call it P of Q, this was calculated exactly for the SK model by Parisi. And for the droplet picture, because it is just two pure states, there are just two possible values for the overlap, plus QEA and minus QEA. And so you get two contrasting pictures of what P of Q should be. For example, in the RSB picture, P of Q has support right at Q equals 0, whereas in the droplet picture, it should vanish right at Q equals 0. The droplet picture is based on scaling ideas at the zero temperature fixed point. And in it, you study the energy cost, or the free energy cost, of creating droplets of linear size L, and these scale with an exponent depending on their linear size as L to the theta. And the surface area of these droplets scales like L to the ds. And in the replica symmetry breaking picture, the surface area is enormous. It scales with the exponent d. So the droplets are space fillings in the replica symmetry breaking picture. Whereas in the droplet picture, ds is less than d. And so you get an interface which doesn't fill the whole of space. And the curse of the spin glass problem is that finite size effects have prevented a convincing determination by simulations of whether RSB or the droplet picture applies. And there's a very nice recent paper by Wang et al. Who went through a whole list of problems which people have studied using simulations, showing that you can fit the data quite well, or equally well, within statistical criteria to both scenarios. So it's very disappointing, is that, because it suggests that numerical work will not be able, in the near future anyway, to resolve the difference between these two theories. One thing which I should make as a passing remark is the Janus collaboration. The Janus collaboration is a collaboration based on using a special purpose machine. It's in Spain. But they, for ease of computation, use plus minus J bonds. But unfortunately, while it simplifies the computer architecture, it enhances finite size effects. So they can get big systems done, but asymptopia is further away for plus minus J bonds. Well, the first part of my talk focuses on interfaces and their fractal dimension ds. And this is a picture in 2 dimensions of an interface. So what's been done here? Well, this is a picture taken from a paper of Hartman and Young for a 200 by 200 system. And what they have done is they've found the ground state of the system, and then with periodic boundary conditions, and then introduced anti-periodic boundary conditions in one direction. That has caused the spins to flip in one region here. So in this region here, the spins have flipped because of the changing boundary conditions. And there's periodic boundary conditions here and here. So this bit here maps into that bit there. So there's an interface set up which wanders around in a way which is typical of a fractal walk. And Koschbach and Weigel have extended this work to 10,000, and you find the ground states exactly in this work. So it's an incredible numerical achievement, I think. And with that achievement, they managed to pin down the value of ds in 2 dimensions to this value here, 1.27319, and search at the last place. And I think this is just an amazing piece of work. Alas, their work does not extend to higher dimensions, because the problem in higher dimensions is NP hard, and these polynomial time algorithms do not work in higher dimensions. So I want to now talk about two RG schemes for determining the fractal dimension ds. These are based on an idea which I think was studied in great detail here in Saclay by Cécile Monthou in 2015. And the first one is called the strong disorderly normalization group. Now, the strong disorderly normalization group in certain circumstances can be exact. There are some one-dimensional problems where it solves the problem exactly. Alas, this spin glass problem is not one of those. It's just an approximation. And I'm going to talk about two algorithms. The first is the strong disorder RG, and the second one is the greedy algorithm. And they're both very similar. They both recognize that when you have a distribution of bond sizes, the bonds which are likely to be satisfied are those which are the largest. And for example, in the greedy algorithm, you find a ground state by satisfying the bonds in order of decreasing absolute magnitude until a closed loop appears. And if one gets one of those, one skips to the next largest bond. And you can find a ground state quite quickly under this approximation. The SDRG, the strong disorder RG, is quite similar in the way it works. And there are many variants of it, and I don't want to get involved in the details of these various complications. Well, having found a ground state using either the SDRG algorithm or the greedy algorithm, you'll find let's call the ground state SI of pi, and then you determine it again with antiperiodic boundary conditions. You call that new ground state SI of pi. And to investigate the length of the domain wall, you form what's called the link overlap, and this quantity gamma, which is 1 minus QL, which is related to the length of the domain wall by this formula here. So if sigma dW goes like L to the ds, this should fall off with L like 1 over L to the d minus ds. So if you believed in replica symmetry breaking, you would want gamma to go to a constant, because then ds is equal to d. If it falls and approaches 0, you think that there is no replica symmetry breaking. So you can, by studying this, you can estimate what the value of ds is, the fractal dimension of the interface. So here's some results based on the SDRG in various dimensions. And in 2 dimensions, we can get out to quite large system size. We've managed to study values of L up to about 1,500. But for 6 dimensions, we're much more restricted. We can only go up to about 14 dimensions. But notice that in all cases, you can fit to a form which indicates that this is quite a decent fit. There's no sign, really, that this is going to level off. Now, of course, by the miracles of curve fitting, you can imagine these curves will level off. This is what you have to believe if you believe in replica symmetry breaking. But there's no sign within this approximation that they're going to level off.
D equal 3 already leveled off, right?
Pardon?
D equal 3 already leveled off.
You can fit to that way, you can fit to this way, and it works just as well. You see, this is an example of why numerical work never makes any progress, because different people fitting similar data come up with quite different conclusions.
You just look at it.
Yes, yes. Well, look at the other plots the other way. Oh, we'd like to talk about large L, but oh, sorry.
I just don't understand the statement that it levels off. It doesn't look like it levels off to me. That's what happened at large log L.
At large log L, if you believe in replica symmetry breaking, it would go like that.
But it certainly doesn't look like it's
This doesn't look like that. But I think Enzo was making the point that in his simulations, up to L equals 16, the rather small systems, he can see signs or fit that it might be leveling off. So, yes, the simulators can't get to these values of L, unfortunately.
But you do have to believe that the SDRG is correct.
That is, unfortunately, one of the things you have to assume, yes. Okay, well, the SDRG, I'm not selling it very well, but in many ways it's a rubbish approximation. It gives very poor values for the exponent theta. It's even of the wrong sign. But in 2 dimensions, it's not bad. It gives this value in 2 dimensions, and we managed to study up to L equals 1600. And the exact value, this is the value obtained by Koschbach and Weigel, this is this value. So it's quite close. For d equals 3, we get this number here for L up to 128, and simulations only go up to L equals 12 or thereabouts, and they give a value 2.57. Now, of course, ENSO would say it gives a value 3, but that's a different way of fitting. Now, if we only had our data up to L equals 12, we would have reported that ds is 2.6. So there's considerable finite size effects, even in context of the SDRG. Well, when we were studying the systems near 6 dimensions, we could only study up to L equals 14, which is really not very big. And you can't really be sure that ds is becoming equal to d right in 6 dimensions. Now, that is why we turn to looking at the greedy algorithm. This is known. It's known for the greedy algorithm that 6 is the special dimension. And this was shown by work of Jackson, Reed, and Sweeney and Middleton. So can we see, using this other variant, basically, of SDRG, the greedy algorithm, that 6 is a special dimension? Well, these are the results for ds plotted against d. The red ones are SDRG, the second one are GA. There's no reason why these two should be the same. They both give the exact answer 0 for ds in 1 dimension, and they're both approaching the point ds equals d as you go towards 6 dimensions. When ds equals to d, this upper limit, which is the bound of the value of ds, is being approached. This is the lower limit of this quantity when ds is equal to d minus 1, which corresponds to a straight interface across the system. So values of ds have to lie between d and d minus 1. And between 1 dimension and 6 dimensions, you cover the range. And both the SDRG and the greedy algorithm are approaching the value ds equals d in 6 dimensions. So I would argue this is indicating that the replica symmetry breaking picture is going to set in a world above 6 dimensions. So, on the suggestion of the referee, who I think is in the audience of our paper, we blew up the data, and I think I'm looking at him now. And it's a very useful suggestion. He suggested plotting it on an amplified scale, and previously we only had this kind of data, and the slope, it had not leveled off, indicating that ds was equal to d in 6 dimensions. But when we got a bit larger, it showed signs of this leveling off. So it looks as though within the SDRG, you can get to system sizes which are big enough to see the onset of RSB. The greedy algorithm settles down much faster and gives ds equals d equals 6 without too much difficulty. So finite size effects, even within these real space RG calculations, are problematic. So let me make some more remarks about the strong disorder RG. First of all, one remark I would make about it is that it can be proven to be exact for a very unusual bond distribution. This is a bond distribution in which the largest bond is larger than the sum of all the remaining bonds, and so on all the way down the line. This is an extreme Levy distribution. And for this distribution, Jackson and Reed showed that above 6 dimensions, it can only have many pure states above 6 dimensions, and only 2 pure states in less than 6 dimensions. So for this weird bond distribution, this scenario which I'm advocating, which applies to Gaussian bond distributions, can be shown to be correct. And somehow it's as though in the world of less than 6 dimensions, phase space is just not big enough to allow for a multiplicity of pure states. And there's other real space RG methods, the most notorious of which is the Migdal-Kavanaugh renormalization group scheme. And this has the result that ds is equal to d minus 1, which means that within that scheme, you never get a transition to a state which has replica symmetry breaking, though you can still get RG flows which might mimic what you think might happen in higher dimensions, as Giulio and Maria Chiara Angelini found. But like all real space RG methods, there are many, many variants which you can invent of the SDRG. Cecile, in her original paper, gave 2, and we've used both of them. And her second one, which we didn't really explore that much, is certainly an improvement over the first one, the one I was talking about, in that it gives better values for the exponent theta, but still leaves the value of the factorial dimension ds almost unchanged. So if this was back in the 70s when real space RG calculations were all the fashion, there'd be lots of people doing different things. Nowadays, I think the enthusiasm for real space RG has died a bit. And what people want to do now is called the non-perturbative RG procedure, which is in many ways just as ad hoc as a real space calculation. And I'll be making remarks about that later on. I want now to turn to the second part of my talk, which is on perturbative RG calculations based on what happens in connection with the so-called de Almeida-Thouless line. And this is advertised as a probe of the existence of replica symmetry breaking. The Almeida-Thouless line, the AT line, marks the onset of RSB in the field temperature plane. So in the high temperature phase, you're in the parametric phase, you cool down, you cross the AT line, and you go into the spin glass phase with replica symmetry breaking. And this is a scenario which you find in the Sherrington-Kirkpatrick model. There is a well-defined line on which the spin glass susceptibility diverges. Now in the droplet picture, putting on a field kills the transition, just as it does in the ferromagnet. There's no phase transition in the droplet model in a field. And I'm arguing that this transition between here and here takes place when at a certain dimension, and I think it is 6 dimensions. Well, can we see any argument for that within perturbation theory? Well, all perturbative calculations effectively start from this free energy functional involving replica fields Q alpha beta. So here's the quadratic term, R changes sign at the mean field transition temperature. This is the bending energy term. This is the cubic term. This is the effect of the field, and there's higher terms. And in principle, all of the spin glass physics is believed is contained within this function. Though at mean field level, it's not true, is that? You have to put in the q to the 4th terms. So using the normalization group, we calculated the position of the AT line starting from this Hamiltonian, but we did it perturbatively, where the small parameter was epsilon equals d minus 6, but we took d bigger than 6 rather than less than 6 as is normal, and we got this formula here, and it has certain interesting features, as we'll see. If you work very, very close to TC, and it's only in this limit is where the formula is useful. If you work in this limit here so that that becomes much, much larger than 1, the formula reduces to this expression here. So if I take these expressions, the WR to the derivative to the left-hand side, on the right-hand side, if I expand out what epsilon is, to d minus 6, you get an indication that something strange might be happening in 6 dimensions. In particular, the AT line looks to be getting flatter and flatter near its tip as you approach 6 dimensions. Well, I was quite pleased with this, but Parisi and Temeshvari pointed out to show that the AT line as a whole disappears. You will need to work at fixed R. And if you work at fixed R, this perturbative treatment doesn't work really. And the argument stops working because in the limit when d goes to 6, when at fixed R, this quantity here just goes to 1, and you don't see anything special about 6 dimensions. But it's very, very hard to do the perturbative treatment at fixed R. You have to have R small to make progress. So this, I thought, was going to be the last one could say about the subject. So I turned to looking at an alternative approach. An alternative approach is similar to what one has in the ON theory, where n is the number of components of the order parameter. Here, if you could look at, say, a Heisenberg spin glass rather than Ising spin glass, m is 3. So that's the 3-vector spin glass, the xy spin glass with m equals 2. And I showed that the value of the field at t equals 0 could be written in this form here, where Tc was the value of the transition temperature for the infinite M spin glass. Now this, unfortunately, is not trivially soluble, as is the large N limit in the case of the conventional 5 to the 4th theory. So you have to do numerical work to work out what Tc is. But it's not very hard numerical work because the problem is not NP hard any longer. It can be done in polynomial time. So people have studied what happens in quite high dimensions. And there is evidence to suggest that the transition temperature in the large M limit is going to 0, which suggests that maybe the AT line might be going away as you approach 6 dimensions. But it does suggest to me that because the large M limit is rather like summing planar diagrams, that people who are doing the non-perturbative RG will probably have to include up to planar diagrams, which is impossibly hard, probably, to see that 6 could be a special dimension. Well, to study the AT line itself, you have to recognize that at the AT line, there's a field going soft, and that is the so-called Repticon field. That's defined by fields which have the following property. If you sum over one index, the answer is 0. And the effective functionale involving these fields is this one here. Now, R tilde measures the distance from the AT line. This is the bending energy term. Now, there are 2 cubic terms, W1 and W2. And in principle, you can calculate what these are from the previous functionale, but to do that, except perturbatively, is very, very hard. It's just as hard as calculating the AT line itself. But near TC, you can make progress. And right on the AT line, you'd expect W1 and W2 just to be functions of temperature. But perturbation theory comes to our aid, and we can make a bit of progress. Now, the first calculations at the AT line were done by Alan Bray and his student Steve Roberts, who worked below the AT line and derived these kind of flow equations here. And alas, they have no fixed point, which is stable. And that led Bray and Roberts to speculate that that might indicate possibly no AT line. It could also indicate a first order phase transition. They didn't know. And Cyrano himself spent a lot of time trying to get round this problem by introducing more coupling constants and so on, but it looks as though you can't avoid this dilemma. There are no stable fixed points describing the Almeida-Thalles transition in a field. So you're stuck with this problem that for d less than 6, you can't find a stable fixed point. On the other hand, for d bigger than 6, there is the stable Gaussian fixed point. So this line here indicates the domain boundary of attraction. So if you start out with a W1 and W2, in this region here, you float the Gaussian fixed point in d bigger than 6 dimensions. If you're outside this region here, you zoom off who knows where. And there are 4 fixed points marked, one here, and one which looks to be on the axis but is slightly off. And the whole size of this region of stability scales down as d minus 6, simply because everything can be rescaled to be in units of square root of epsilon. So I've blown up that region near the origin. Now, this is the Gaussian fixed point. A flow which starts out on the boundary would go to the point Z, but if it's slightly off the boundary, it goes along the boundary and then veers away close to this orange line which connects Z and G. So there are 2 stable eigenvalues in the W1 and W2 space at fixed point, the Gaussian fixed point G, and there are 2 unstable fixed points at the value I've called U, with no stable eigenvalues, and there's a fixed point Z, the one I just showed, which is nearly on the y-axis, the W2 axis, which has got 1 stable eigenvalue corresponding to flows along the boundary and an unstable eigenvalue off it. And all RG flows on the boundary go to this fixed point Z. So I've added to this diagram here what the green line, and this green line indicates is a schematic line, possible values for initial values of W1 and W2. So if the W1 and W2 on the AT line are just functions of temperature, so it could be that at one temperature you're in here, and that will take you, then if that case you'll flow back to the Gaussian fixed point. If you start out here, outside the domain of attraction, you'll flow off to infinity, and right on the, where the line cuts the domain of attraction, the flows will take you to this fixed point Z. And this will lead to the following story, where there is some kind of multicritical point on the AT line itself. So we can show that for near to TC, you will be in the regime where you're inside the domain of attraction, and the exponents at the AT line will be those associated with the mean field theory. If you cross the AT line here, you have a starting point which will be outside the domain of attraction, so who knows what goes on, and there'll be a special point, a multicritical point, on which you will see non-trivial critical exponents in one particular direction. Now, of course, this is just one possible scenario. There could be a phase boundary coming out here as well, which would separate a completely non-perturbative spin glass from a perturbated spin glass. But we've used some kind of Occam's razor just to have a unified spin glass phase and just have different exponents on crossing the boundary. So if you were interested in the exponents of the critical fixed points, you have to look what happens at the fixed point z, and from the values of the fixed point z you can work out eta associated with the multicritical fixed point, and eta is given by this value and it's equal to numerically to this number, and nu is given by this number here. But people who do numerical work, I wouldn't dream of attempting to check this out, because there's so many crossovers going on, there's no chance. But what you can probably see by doing numerical studies is what happens in the non-perturbative region. Anyway, I want now to show that indeed that there is a multicritical point by calculating the transition temperature of the multicritical point. And to do that, we have to estimate the initial values of these coupling constants W1 and W2. So we can do that by integrating out all the couplings up to a length scale 1 over xi, where xi is the correlation length in zero field. Now, the remaining replica modes can still be critical, provided we are close to the AT line. But from this approach, we can get the initial values of W1 by this device here. This is the zero field RG flow for the coupling of the first functional. And from that, we can work out what happens at length scale L. And it's falling off according to this formula here. And when given this regime here, the coupling constant gets small according to this formula here. Now, this is the perturbative result for the value of W1. It's only valued very, very close to TC, rather in the same regime as where the calculation which I did with Alan Bray was valid. And W2 is even smaller because of this order of magnitude. So the coupling constants W1 and W2 lie inside the fixed point, provided the initial temperature measured by R is such that W1 is smaller than the value of the coupling constant at U, which is square root of epsilon over 24. That fixes R to be less than this number here. So as epsilon goes towards 6, this is an incredibly small number. So it implies that if D goes to 6, the multicritical fixed point moves towards TC. And in this limit, the entire AT line becomes non-perturbative. Now, of course, you can ask what happens as you move away from 6 dimensions, go up towards 8 or 10. Well, presumably, TMCP will move away from TC, and we suspect that it will eventually go to 0. And so maybe in high enough dimensions, say 20 dimensions, it disappears altogether. Certainly, there's no hint of a multicritical point in beta lattice calculations or anything of that sort. So you would only expect to see the existence of a multicritical point in dimensions, say, below a certain value, whose value we do not know. Another thing which has not been determined is the actual form of the AT line below TMCP. So we can calculate it up to this point using the Bray-Moore previous formula, but beyond that point, we don't know how to calculate what the AT line, where it goes. This remains an unsolved problem. So let me just conclude. I've talked about two related algorithms, the SDRG and the greedy algorithm, which provide evidence that there's a fractal dimension ds approaches D in 6 dimensions. So there is evidence for replica symmetry breaking, as you approach 6 dimensions. And consistent with that, we found evidence using the perturbative RG that 6 also might be a special dimension, at least for things to do with the AT line. Now, my belief is that what happens is the AT line simply disappears as you go to 6 dimensions and doesn't reappear below 6 dimensions. There's a scenario by Charbonnet and Yaida who said it pops back up again in some dimension like 5.3 with nothing in between 5.3 and 6. But I really don't think myself that's too likely. And I think if it goes at 6, it's not going to come back. It's dead. And I think what we need now are new calculational methods. In particular, we need to work at summing lots of diagrams, in particular the planar diagrams, which I think will reinforce, should they be summable, this scenario. But I don't think one can really hope to sum planar diagrams in finite dimensions. Maybe it's only possible in 0 dimensions. Well, thank you very much.
Yes. I would have a question and then a comment. Could we go back one moment to the figure I was asking about, just to try to understand, because maybe...
The one involving gamma?
Yeah, right. The one, yeah. Yeah, before, I believe. Yes, next.
That one?
You see, yeah, my point was that, look at the first line, right? This is d equals 6 and it's clearly saturated. So now, clearly, on this L, that are very small, by the way, right?
Yeah.
On this L, if you look 3, what is 2, it has to go down. We know in 2 there is
this is 2, this is 3. Yeah.
3 and 4, you would say is going down, you don't know. But look at 5. This is very interesting. Would you claim that d equal 5 is going down? No, it's not.
Yes,
d equal 5 is not going down. You look at the curvature, you will do any honest, reasonable fit, and you will find that d equal 5 saturated. So you have shown here that you can establish with very small size that d equal 5 is replica symmetry breaking. And obviously, from this figure, I cannot say anything about 3 or 4. So that was my question. Then I would have a comment. I can do a comment now. I think tomorrow I have a very short talk, maybe in 5 minutes. I can give some ideas. I don't want to give them now because that would just spoil it, about something that can solve the day for everybody. And also that there are at least 2 sets of papers that are relevant. I mean, work of this kind about a direct measurement of the surface of the domain has been done many years ago in a series of papers with Imre, Alain Milloir, Andrea Majorano, and we find the different results when you find, that is, we find ds equal 3 in 3 dimensions. And also, there is a paper, beautiful paper you wrote that I had the honor to co-author with you, right? In which we see clearly that when you increase the size of the lattice, the number of states increase, okay? And this is not so much droplet light, but okay, this was only a comment, while this is a question about what do you think about that.
Well, the beautiful paper we wrote was on the SK model.
Yes. Okay.
Yes. Well, we've had this discussion already. If you have a small, if you're working in 3 dimensions and doing a good job, you limit it to very small system sizes. And you just cannot get a range of system sizes.
No, I agree, but I'm asking about d equal 5 in this picture.
Well,
d equal 5. The blue points just under the red, because you are doing a strong point about d equal 6, but you are showing us that in d equal 5 there is replica symmetry.
well, let me just move on to this one here. No, this one. This is d equals 6. Now, with a small system in d equals 6, it was coming down, but eventually it leveled off. So there is a chance in this kind of numerical work that you can see this leveling off, which is the hallmark of RSB. But in 3 dimensions, that has yet to be achieved, I think. And never will be, is my opinion.
This is my point of tomorrow.
Oh, you'll have achieved it by tomorrow.
Okay, so I think the SDRG and the greedy algorithm strongly underestimate frustration in the system, as usual. So don't you expect that with this strong underestimation, it's normal that you don't get replica symmetry breaking?
Well, why do you say they underestimate frustration?
From the experience, if you take the traveling salesman problem, which is obvious if you do the greedy algorithm, you always go to the next one and you don't allow for big loops which would violate and where you will find the strong, the best bond very far away. So you.
But in 2 dimensions, it gives quite a good answer.
But it's not NP complete. It's the phase space is much simpler in 2 dimensions.
Well, it is, but I'm not sure the frustration argument wouldn't extend to 2 dimensions as well.
Last question.
Well, if you are staring into spin glasses long enough, spin glasses start to stare back into you. I have gone through that experience, and therefore I tend to look at the world through that glass, the spin glass. And what I see is that a lot of complex systems, starting with a cell, the brain, society, or the economy, or whatever, are composed of elements between which there are these contradictory or ferromagnetic and anti-ferromagnetic interactions. And without an exception, these systems can sort of, these are finite size systems, they can spend a certain time in equilibrium and then they go over into something else. Concerning the system of checks and balances, we are just witnessing that in Italy, in Hungary, in the US, everywhere. They're spilling over into another relatively stable state. So I think this whole spin glass question of there being a large number of relatively stable ground states, or just 2 of them, boils down to your worldview, sort of. Now, do you really believe that the relevant application of these ideas is the copper manganese? Frankly, I don't.
Well,
I don't care about much.
I think it's an interesting point. If you're interested in the properties of this alloy, manganese in copper, and who is, but if you were, this is what you should be talking about. But people have found that the extension of spin glass idea to these other problems, which is usually based around Meafield ideas work well, or is the appropriate language, it's much more interesting. So, but out there, I remember coming to Orsay in the 60s and 70s, where there were people making these alloys, and people would say, well, erbium and terbium is not the same as silver in gold and stuff like that. Or no, it wouldn't be silver, iron in gold. So there was at one time a whole generation of experimentalists who were interested in spin glasses. Sure. No one's interested in spin glasses any longer. They're interested in these extensions to which you were alluding. And for them, all this stuff about 6 dimensions, or not, is not of interest.
This is what I wanted to say.
Okay, so last one.
A naive question, Mike. Is there an a priori estimate of the size of the critical region? Of the, I mean, a Ginzburg criterion or something?
Well, there will be one. Yes, I think in 3 dimensions where presumably we have the best estimates. There is no, Enzo, you probably know, there's no sign of a mean field outer regime and close in a critical regime. The critical regime fits over all, no one's thought that was a good way to fit the data. So if there is a...
Yeah, I don't know if this will answer, but I mean, somehow it is that all the broken physics treat them.
So it's a bit like the two-dimensional Ising ferromagnet of von Saga. There's no region visible which, in his solution, which looks mean field-like. So I'm sure the Ginzburg criteria might work in higher dimensions, but not in the dimension which will be most explored, which is 3 dimensions.
I see. I'm sorry, I think we should go on. So let's thank Mike again. Yeah.